Chapter 3 Propagation of Error. The objectives of this video are to define bias, uncertainty, accuracy, and precision, and to calculate bias and uncertainty. As a difference from the previous chapters, in this chapter we are measuring something instead of simply drawing samples from a population. Measurement error. Any measurement procedure contains error, hence all measurements differ from the true value. Errors in the measurement produce error in calculated values, like for example the mean. The error or difference in the measured value is the difference between the measured values and the true value. The definition of propagation of error. When error in measurement produces error in calculated values, we say that the error is propagated from the measurement to the calculated value. Parts of error. Measurement error has two parts: systemic error or bias, and random error or uncertainty. The bias is constant for every measurement. For example, the scale that is always off by 2 grams. On the other hand, uncertainty varies from measurement to measurement and averages out to 0 in the long run. The measurement is the sum of the true value plus 2 parts of error. The measured value is equal to the true value plus the bias plus the random error. The true value plus the bias, it will be the mean of the measurement, and the random error is represented by the standard deviation. Parts of the error. The first one is the mean. The mean is the true value plus the bias. Now, the bias is the difference or error between the true value and the mean. The bias is the mean minus the true value. Now, accuracy is defined in terms of the bias. So the smaller the bias, the more accurate the measurement. So bias is related with accuracy. Now, precision is relative to the random error. So the smaller the uncertainty, the more precise the measurement. In conclusion, the measured value is equal to the true value plus the bias plus the random error. And remember that the true value plus bias is the mean, and the random error is the standard deviation. Bias and uncertainty. Let's suppose that we have the following sets of measurements: A, B, C, and D. In each one of the cases, the measurements are given by the dots in blue, and the true value is indicated in each one of the cases. Analyzing the data sets, we can also find the mean of each one of the sets. To locate the mean, we have to look for the middle point of the data sets. In this case, will be very close to the true value. In case B, it will be a little bit to the right. In case C, it's also going to be very close to the true value. And in case D, it will be to the right. That's the average of the points in blue in each case. So we can see that the points on the left, the distance of the mean to the true value is very close. So these points have a small bias, and therefore they have high accuracy. The ones on the right, however, the distance to the true value is much larger, and therefore they have large bias and low accuracy. On the other hand, if we look to the standard deviation of the data, so this is how much the data is sparse around the mean, so that's sigma. In this case also we have sigma, and on the right hand side we'll have something like that, sigma and sigma. So what we can see is that the data sets in the lower part, sigma is very large, and on the top, sigma is smaller compared with the ones on the bottom. So the two on the top have a small sigma, therefore they are precise. The ones on the bottom, they have large sigma, large standard deviation, and therefore they have low precision. This is another example of accuracy and precision. The true value is represented by the center of the target. In the first case, we can observe that the mean of the points are located at some distance from the center, so this will represent the bias, and in this case the bias is large, so it has low accuracy. However, we can observe that the points are close together, so in this case we'll have also a high precision. In the second case, we can observe that the points are very sparse and the mean of this point is located also at some distance from the target, so it neither have high accuracy or precision. So in this case is low accuracy and low precision. Next case is very accurate and very precise. So it's high accuracy and high precision. And in the last case, even though the center or the mean of the points is very close to the target, their points are sparse. So we have high accuracy and low precision. Bias and calibration. So when we talk about calibrating an instrument, we are talking about bias. So if we want to reduce the bias, or we want to know the bias, well, we want to know the true value. So what usually happens is that you have to have a standard element in which the true value is known. So then you can compare. So in the process of comparison is calibration. So calibration is a process of determining the bias of measurement. The smaller the bias, the more accurate the measuring process. Uncertainty. How to reduce the uncertainty? Well, we have to repeat the measurements in order to estimate the uncertainty. Let's see, for example, we have our data set. Let's say the true value is here, and then we have our measurements. Mu will be somewhere over there. So we have our bias, which is the distance from the mean, and the uncertainty, which is how close together are the points. Now, if we start doing some measurements, so we are going to have this type of curve in which we have the mean, and if we measure the standard deviation for this case, we're going to have mu minus sigma and mu plus sigma. If we keep increasing the number of measurements, so we are going to reduce the standard deviation, so that will be mu minus sigma in the second case and mu plus sigma. And finally, when we increase the number of measurements, we are going to have this distribution, so that will be mu minus sigma and mu plus sigma. So in general, a measurement, it will be mu plus or minus sigma, and sigma is decreased as we increase the number of measurements. The tension strength of one specific concrete is known to be 50 megapascal, so that's the true value. A student runs 5 independent measurements and gets 51, 47, 53, 53, and 48 megapascals. So we have to estimate the bias. So the measurements are 51, 47, 53, 53, and 48. So we have 1, 2, 3, 4, 5. So n equals 5. and we need to estimate the bias. So first of all, we need to compute the mean. So the mean is equal to 51 plus 47 plus 53 plus 53 plus 48 divided by 5, and that's equal to 252 divided by 5, and that's equal to 50.4. So that's the mean of the measurement. Now the bias, by definition, is equal to mu minus the true value. In this case, mu will be given or approximated by x bar, and so this is equal to 50.4 minus 50, the true value, which is equal to 0.4, and that's the bias. Now, how do we estimate the uncertainty? Well, the uncertainty is the standard deviation, so by definition is the square root of 51 minus the mean plus 47 minus the mean is 50.4, and all of these are square, plus now we have 53 twice, so 2 times 53 minus the mean square plus 48 minus the mean square, and everything divided by n minus 1, so 5 minus 1. If we input this in the calculator, we are going to have that the uncertainty is 2.79.